So I'm very pleased to introduce our first speaker, Seth Grimes. Seth consults on product and market strategy for natural language processing, text analytics, emotion AI, and digital transformation via the Alta Plana Corporation. Seth's a former luncheon speaker of the ASA way back when. He also runs the NLP and DC NLP meetups, and he organizes the Emotion AI and CX Emotion conferences. So I'm very excited to announce our first speaker, Seth. Take it away.
Great. Thanks very much, Adam. I'm pleased to be here today. So I actually am near Washington, D.C., but I got lots of Chicago ties that I'll describe in a moment. So today's talk, at Adam's suggestion, is NLP 2020, What Works and What's Next, Recent Advances in Natural Language Processing. It is a boil the ocean type of topic, natural language processing. There are any number of perspectives one can bring to it that range from a data scientist or software developer perspective to a researcher or scientist who is developing the methods, a linguist who is very much interested in how a computer might understand and produce language, which is, before the age of computers, of course, an artifact solely for humans for their communications. So I will introduce myself further by saying I do consult on product and market strategy around natural language processing, and especially emotion AI and sentiment analysis and other AI applications. I have other activities. For instance, yesterday I had a monthly roundtable on artificial intelligence that I facilitate for a local, for the Maryland's Technology Development Corporation. As Adam mentioned, I run a couple of meetups. You're welcome to join them. I don't believe there's actually a Chicago NLP meetup. I'm very much looking forward to going back to in-person events because I love the inner exchanges that you can have with other people. But I did move my meetups online back in March, and they've been very successful. So if you're interested in natural language processing in usually technically oriented talks, you can join one of those meetups or find another you can join. I do some writing, although I've done a lot less the last couple of years. And as Adam mentioned, I organized a couple of conferences. And I did give a talk 11 years ago to the ASA Chicago chapter. I remember visiting Chicago and giving that talk, which was facilitated by John Vanderploeg, who is I saw on the Zoom today. We held that at an advertising company, and I remember the room was full of cigarette machines and cigarette advertising. So I don't think you could do that. That was only 11 years ago, but I don't think you could do that today. I have had a consulting client, eContext in Chicago, and my son went to Northwestern and lives in Chicago now, although unfortunately he's gainfully unemployed because he works in theater, and there isn't a whole lot of theater going on nowadays. So I hope that will change soon. So that's a bit about my background. And before we really get into it, a disclaimer, which is that I'm going to use a lot of commercial product materials in the slides that follow. These are illustrations and they are not recommendations. I'm not going to show you anything that I don't believe in, but I just kind of figure, why spend the time making up my own graphics and materials when other people have already done it? And that applies to the numerous academic and research papers that I will cite using images as well. Any one of these individuals does what they do better than I do. So why not use their words and their images? And at the same time, the advantage is that you will have places to go look to research further the kinds of topics, that I will be bringing up and talking about. So my background, once again, is technical in databases and application software development. For instance, in the statistics world, one of the jobs I had was for 4.5 years at the US Census Bureau, building the analysis tabulation system for the 2000 US Census using SAS statistical programming tools, as well as a lot of scripting and some specialized cross-tabulation software. While I have done a lot of software work in the past and database work, I'm not doing that currently. Mainly I study what other people do, including at the interface between research and science and commercial product implementations. But in accepting to do this talk, I decided, well, initially I had suggested a talk on emotion AI, which is a specialization of mine. But then in exchanges with Adam, it seemed like, well, why don't I take on doing a broad overview of recent advances in natural language processing for this talk. So my emotion AI content, as well as content on conversational interfaces, will be part of this talk toward the end. I'm going to be starting off by some level setting about natural language processing. Let's move there right now. And then talking about software, I will talk a lot about those recent advances, the stuff that we all have heard about, starting with vector space models, word2vec, and further implementations of that, then transformer models, different transformer architectures, I should say, and transfer learning in particular. Then I'll talk about some software implementations, once again, using numerous examples before getting into those two application areas. Looking at the program, you're going to have additional talks that apply NLP. Shlomo Argaman, I've had speak at conferences that I've produced at least a couple of times in the past, and I've worked alongside him a bit in one consulting gig. And I am familiar with his work on stylistics. I'm looking forward to that. That is an application, of course, of natural language processing and a specialization of it. So I don't need to cover that, nor do I need to really cover the conversational interfaces, because you'll get some of that in one of the subsequent talks focused on a specialized area. So that's what I'll be talking about. But let's start with a bit of level understanding, natural language processing. It really consists of two things, goes in two directions. One direction is understanding and the other is generation. I am generating natural language right now as I'm speaking, and you are, I hope, understanding what I'm saying. If I were speaking in Urdu, for instance, however, which I can't, then maybe you wouldn't understand because you don't understand Urdu. So there are immediate challenges that there are many human languages. I had a conversation with a scientist named Rohini Srihari probably about 10 years ago about Urdu versus Hindi. In particular, they are really the same language, 80% the same language, but they're written with different scripts, and they're written, they're spoken in different settings, both religious and national settings, Pakistan versus India. And their idiom in the two languages does not overlap so much, I learned from Rohini. So we have to be able to understand all sorts of nuance that is involved in language, including idiom, multilingual situations, and so on. Now, there are a number of perspectives we can bring to this. Natural language understanding includes, well, basic stuff like optical character recognition. If we have texts that we need to computerize that has been written out, it isn't originating in the computer. Language detection, am I speaking English, Urdu, Hindi, or actually some mix there? Tokenization is the idea of breaking language up into pieces that then become amenable to further analysis. Tokenization might split language up into words, or it might chunk it into groups of words. Parsing is something that many of us in the United States, at least, learned in junior high school, where you created sentence diagrams. But parsing goes beyond that to handle different types of chunks of language. Natural language understanding includes information extraction. This is really a core part of what we're trying to do here. We do get to parts of speech, what you and I might have done in junior high school with sentence diagramming. Chunks are composites of things that go together. It might be an adjective that goes with a noun. Entities can be the names of persons or places. Aspects are elements of those entities in maybe a hierarchical view, a component or something like that, topics, themes. Relations, how is one thing related to another? If I talk about President Trump, which I hope not to be for much longer, the relationship is that Trump is the president. You can call that an attribute if you wish. An event is a specialized type of bit of information. There are many other types of information that one can seek to extract with natural language understanding. Then we have speech processing. Speech obviously involves sound. It involves phonemes or different components that are broken out, but it also involves a bit of delivery that goes beyond the textual components and the sound components. That can include things like the rapidity of my speech. Well, we'll get into that later. Natural language generation on the flip side, and I will shout out to Chicago company Narrative Sciences, that is a pioneer, that was the first company I encountered with natural language generation, is the flip side, where we use computers to generate language. I believe there's a speaker later on this program who's going to be talking about one of the, well, certainly the biggest and the leading edge model for natural language generation. So I'm not going to talk about that. And then we do have natural language processing tasks that combine understanding and generation. Summarization. We take a long text and we need to understand it in order to produce a shorter text that keeps the sense and meaning of what we're summarizing. Machine translation from one language to another, understands in one language, generates in another. Conversational interfaces, back and forth, obviously understands, understanding and then generating. Question answering is similar. Sorry, I lost my focus. Oops. So what about functions? So here I'm calling on a survey, and I'll have a few more slides later on that use this survey that was recently launched by Ben Lorica at Gradient Flow, looking at the natural language processing industry. This was sponsored by John Snow Labs, which is a software producer that I'll talk about just a bit later. What are people trying to do with NLP? You can see this yourself, and I will be sharing my slides. They're already posted on SlideShare, and I will paste in a link for that later. But named entity recognition, one of the things I was talking about on the list there, I mentioned in passing sentiment analysis. Document classification is at the top of that. Just sticking stuff in bins. I'd make the argument that just about everything we do in the world of statistics is either categorization or classification. It's either discovering categories via potentially statistical methods in source materials and then sticking stuff into those categories. And that can include documents. In arguably named entity recognition is a form of classification, and so is sentiment analysis. So you can look at this stuff yourself later. I have a ton of slides, and so I'm going to be moving through them very quickly. So I would argue that this is the actuality of the natural language processing world. This is a picture called the Garden of Earthly Delights. It very much to me captures the variety of human activities and human interactions and all of the wonders that are out there, as well as maybe some darker elements. So just to finish that level setting business, natural language processing is a garden of earthly delights. And to substantiate that, I have pasted in a list of higher level topics that are being discussed this week at a conference called EMNLP, that's Empirical Methods for Natural Language Processing. It is one of the leading conferences in this world. It is in academic and scientific conferences. So you can see the variety of things that are going on in the research world for natural language processing. Many of these are most of these are implemented already in commercial offerings, some of them not particularly well, and some of them not quite yet. So I really love certain things that are on the leading edge. For instance, argument mining or discourse analysis. These are discourse and arguments are things that are sequential, that can involve multiple parties, that can have an evolution of ideas. We're not just dealing with some static document. We're dealing with a meta structure of the communications and not just the words that are going on. So there's a whole variety of stuff going on in the natural language processing world. Let's do a little bit of history and as a way of getting into some of the technologies that have emerged in the last couple of years, the last 5 years, say, the recent advances. I'm going to take us back to 1958, which I'm characterizing here as early days. Of course, computers only started to become widely used in the 60s, I would say, in the business world. In any case, this is screenshot from a paper by someone named Hans-Peter Lund, published in the IBM Journal in 1958, a business intelligence system, the first use in a modern context of the term business intelligence. He talks about, I added the red ovals you'll see here. He talks about transcribing and encoding, because he was starting with paper documents because our routine business interactions and transactions were not computerized. And he talked about abstracting. Of course, that's a key thing. It's what, for instance, a librarian might do in putting something into a catalog. An abstract, what is this thing about? Not just the title. In the center part, in what Lynn calls the comparison area, he has certain questions that are really fundamental to knowledge management to this day. Who needs to know, who knows what, and what is known? So we start even back then with the idea that we handle language in a natural native form, in this case written, we transcribe it into a machine, and we try to extract knowledge from it and that is going to be usable. Another shot from a different paper of Lynn's from 1958, where he talked about statistical information derived from word frequency and distribution. That word distribution is key here, is used to compute a relative measure of significance. Now, this can apply to abstracting, or summarization is similar to abstracting, where you're trying to look at the really salient or important parts of a given bit of text. So Lynn talked about statistics. Statistics is the first way that people really tried to use computers to make text tractable, to make it computable, to make it something that you can extract information from. And just think about it. The frequency of my use of words and multi-word terms, let's call them n-grams, one form of n-grams, is an indicator of what I'm talking about. I'm going to use natural language processing a lot. That's what my talk is about, surprise, surprise. So this stuff dates back to 1958, and now I get to deploy one of my favorite quotations that I'm guessing the majority of you have seen, the statistician George Box, all models are wrong, but some are useful. That very much characterizes language models. I would say that no single language model is correct, except maybe for a very limited usage. If it is going to be perfect, then it is going to be brittle and rather than robust, but they're useful and they are advancing. So I'm going to fast forward 17 years from that 1958 Lynn quotation to 1975. I stuck in a copy of my slide from my 2009 ASA Chicago talk, talking about vector spaces and Salton, Wang, and Yang's vector space model for automatic indexing. And then in the lower left, I have a term document matrix, which is how one might deal with vectorizing the words within a document in order to apply an algorithm such as TF-IDF, term frequency, inverse document frequency, how frequently something occurs. Again, we're counting stuff here. How frequently something occurs relative to its frequency within a much larger document set in order to facilitate information retrieval, in order to give us a ranking algorithm for information retrieval. Of course, that's not the only ranking algorithm, and sticking stuff in a vector space is not the only method that one can apply to model text and make it useful. So I have listed 4 of those here at a very high level, and I'm going to gloss over them. I'm not going to cover them in any kind of depth. We'll say that rules, that can mean capturing syntax. Taxonomies have been around for thousands of years. The animal kingdom, for instance, is an example of a taxonomy. It's hierarchical and categorizes stuff. Boolean expressions you're familiar with, and then sequence models. I have jumped forward, way forward here. Recurrent neural networks and long short-term memory networks are ways that in particular we can model text. I'm going to dismiss those 2 and not talk about them, but I'm going to give you an example all the same of why text is particularly susceptible to modeling via sequence models. I'm going to quote something. To be or not to be, that is the, what's the next word there? I'm guessing you all know. It's a quotation from Hamlet. If I were to capture that particular quotation in a computer, well, that would be an example of extremely precise fitting and a model that is brittle rather than robust, because you can't use it for a whole lot else than predicting that the last word is question. That is the question. But we understand that, that language is sequential. If I clap like this, I'm guessing that you know what comes next, because we have these sequences drilled into our heads. Okay, so dismissing that stuff. Now we get to recent advances, and I decided to define recent as 2013 with Word2Vec, published in a paper by Google. As I mentioned earlier, will cite numerous papers, and I will give you the URLs so you can go out and look at them yourself and read them if you choose to do that. The key behind Word2Vec is sticking stuff in a vector space, but using a more sophisticated way of representing them than what you saw in the Salton paper from 1975 that I showed. And in particular, we're interested here in the relationship between words, in the similarity of man and woman, king and queen, and that you can transform from one set of similarities to another. You can project from one set of similarities to another. So we capture certain properties and hierarchical structure of data here, for instance, in the country capital that you see in the lower right here, with methods such as this. So we're having a much more sophisticated application of a vector space method to represent words and to understand their associations and similarities. Because here, quoting a linguist, J.R. Firth, 1957, "You shall know a word by the company it keeps." We're interested in distributions here of words, not just words in isolation. Jumping forward just a little bit, I'm sorry, I have one technical slide on Word2Vec. How does it work? Instead of the bag of words where you just toss all the words in a document into a bin, into a bag, and then look at frequencies and so on, you have a continuous bag of words where and skipgrams where you're looking for windows from which you can understand what a word is, and from which you can, a window of predicted words associated with a given word. It's not my intent here to get into these technologies. I'm trying to tell a story that progresses us to where we are now with actual software implementations. So Word2Vec has certain deficiencies, in particular that you lose the ordering of words and semantics. So we have progressions, attempts to represent not just individual words, but sentences, phrases, documents, whatever. Doc2Vec came out as an example of that. And it featured fixed, I have highlighted certain stuff in here, fixed length feature representations from variable length pieces of text. Well, there are certain deficiencies if you're going to insist on fixed length representations that, for instance, a long text might not be captured very well in a shorter representation. So we do have continued evolution here in order to refine these things. So now we have other problems, though, that one of which is sense. There are, in English and in most languages, a given word can have multiple senses. In some languages, those senses can be disambiguated via the tonal properties of the pronunciation. In other cases, it must totally depend on context. The great example here that linguists love is possibly apocryphal quotation attributed to Groucho Marx. Time flies like an arrow, fruit flies like a banana. Well, the word flies has two very different meanings here. The first, time flies like an arrow, that is the action of flying through the air, and fruit flies, well, that is a type of insect. So we need to disambiguate multiple word senses, and we have embedding methods that allow us to do that. Sense2Vec is an example of that, and please do look further into that if you wish. So going on a bit, I love that.
Really quick, Seth, we had a question in the chat from Amayan. Amayan, what was your question?
I don't see the question here. I see Vinod Cherian.
Yeah, it was sent to me privately. It was can we n-grams, I think.
Yeah, can we use n-gram for text extraction?
N-grams can mean different things to different people. For instance, it depends on what size pieces you're interested in. You can consider a word to be an n-gram where each letter is the gram, the little piece, you can have multi-word expressions that compose an n-gram. So for instance, what I have the screen right now, I have names such as Barack Obama, Mitt Romney, Sarah Palin. Those are bigrams, let's call them. They are two-word elements that should be considered on their own. It's pretty clear who Bill Clinton is. It is completely unclear who Bill is. So we consider collections of words as n-grams, multi-word chunks. We have this concept of chunking that I used that term earlier. I suppose n-grams are an example of chunking, except that you have a standard size length typically when you're dealing with analyses with n-grams. I think that's all I really want to say, both because of time and because this is not my area of expertise. So I'm going to move on. So I was starting to say there are many software providers out there, and Explosion AI, which is the producer of Spacey, a natural language processing toolkit. It has one out here that I love that applied sense. And in particular, I like this because it accommodates temporality here, the understanding that the sense of terms in terms of the context of the other terms that surround it can change over time. Between 2015 and 2019, the associations with the name Donald Trump changed before he became president. Mike Pence doesn't appear on the 2015 list. Sarah Palin doesn't appear on the 2019 list. So you can go out and play with these things yourself. So what is the prevailing architecture here? This really gets to the current state of things, although the way that this has been implemented has changed. The current prevailing architecture is an encoder-decoder architecture. This is great for transformations of the type that I mentioned, machine translation, summarization, question answering, where we take language, we encode it and into tokens, and then we can use these neural network methods in order to do that. And then we have an attention mechanism which specifies what types of chunks we're looking at here, what the context window is around a given word or term, and then decodes that, sticks that out into some other space. So we might encode from English, and we need to and then decode into French, but the given idiomatic expression in English might have a certain number of words associated with it that is different from the number of words associated with it in French. We need to understand that something is an idiomatic expression or a name that is composed of multiple words, and we get the sense of that by looking at the context around that drawn from a window of other terms. So this is the prevailing architecture that is being applied, and what has replaced the conventional neural network methods here in these implementations of sequence models is this transformer architecture. So this appeared in a paper that you can once again look for from 2017 that described the transformer architecture that revolutionized the use of attention mechanisms to solve the problem. Instead of taking each element of the input sequence in a given order, we look at the whole sequence as a piece, and we look at multiple sequences in parallel in particular. So I'm not going to go into any more depth here because I'm not a scientist or a researcher, and I think that you'd be better off looking at these materials directly yourself. But I want to give you a sense of the roles and then how they're implemented in software implementations. There's a nice paper out that I believe is from earlier this year from Hugging Face, a whole list of authors associated with the company that I cite in the upper right of this particular slides on transformer architectures that you can go out and look at yourself if you want to pursue this one further. The particular implementation that transformed, that really established transformers is BERT. BERT gave rise to quite a number of variants that I'll talk about in just a moment. Bidirectional transformers, that's an encoding and a decoding for language understanding. So a key point here is that we have pre-trained models that will then facilitate transfer learning, which we'll talk about in a slide or two. So BERT unleashed this idea of creating pre-trained transformer models. It has given rise to a whole ecosystem of other stuff based on the Sesame Street character names. As you can see here, this slide is actually, image is actually from like a year ago, so there's more to it than you see here. For instance, GPT-3 from OpenAI was launched. Another speaker later in the program will be talking about that, so I'm not going to worry about it. My key point is that there's a whole ecosystem of pre-trained sequence models that are suited to different tasks, that are suited to different domains. A key element of research here, by the way, is not captured in the slide, which is the concept of distillation, because some of these models are just absolutely huge, and that becomes difficult to implement them. So we try to really look for the salient elements that preserve the predictive power of a given model with minimal loss, but that perform a whole lot better. So we have pre-trained models, a whole variety of them for different business tasks and problems. Well, actually, what we seek to do is to take generic models, pre-trained models, and to make them adaptable to specific tasks via transfer learning. So the idea behind transfer learning is that it is last mile type of training. A model handles a generic task. The word network is used here because of where I stole this image from. And we do training on a very limited amount of data. This was an innovation that came out of Allen AI, Allen NLP, with their Elmo system, to make a model trainable from a generic model with a very small set of label examples. So here's a paper that describes the use of pre-trained word embeddings that are then used to via transfer learning to make them suitable for a very much more specific task. So once again, I'm providing my slides. You can read this text yourself. You don't need me to read this for you, and you can look into it further yourself. I have just, I think maybe one or two more slides in this area to just reinforce the idea of word embeddings and transfer learnings, that we can then take a much more limited set of labeled data to last mile train pre-trained models for particular tasks that are of concern to us in particular business domains. We do have a profusion of models, which I will describe in the next section of this talk. And so it's interesting to see tools like this language interoperability toolkit, which I learned about only a week or two ago, to study how well a given model is going to perform for a task that you are going to have in front of you. So one of the nice things about natural language processing is we are talking about natural language, and if you understand the language being spoken or analyzed, then you can understand pretty quickly whether the computer's interpretation is incorrect in some way. Well, this is the kind of harness framework that is going to allow you to systemize that evaluation. So I showed that we have a variety of transformer architecture implementations that descend from BERT and so on. So I will go back to my garden of earthly delights here to talk about the variety of software implementations that are available for that. And here I will refer to, I will pull a slide from the survey that I mentioned earlier that was commissioned by the people who published Spark NLP, by John Snow Labs. I gave a talk at their NLP conference on emotion AI, my talk a couple of months ago, and I need to disclose that they are a sponsor of my New York NLP meetup, which that disclosure out of the way, I'm using this slide because it's interesting in showing you the variety of, in this case, open source software implementations that are out there that provide pipelines and frameworks for the different models that are available. Some of these are quite old, actually, in the standard of things nowadays. NLTK, the Natural Language Processing Toolkit, dates to 2002, I believe, is a Python implementation that is still used by a lot of people for learning purposes because of the functions that it carries out, but it doesn't have the richness and robustness of model handling that some of these others do. So you have a variety of options available here that are open source. Some of them are freemium type models where if you want something specialized, for instance, an implementation that is trained for medical and healthcare domains, then you pay extra. But in any case, these are things that you can download and you can work with in Python, sometimes in R or other languages. Go back here, the bottom one there, RASA NLU. It was interesting to see that on this list with 10%, because this is actually a toolkit for conversational interfaces. So I thought it'd be interesting. I'll refer to it later. I'll talk about it later, but I thought it'd be interesting to look at it now for one particular element to see the interlocking nature of these products that are available. So as you can see here in the text, RASA actually uses the Spacey NLP library, and in order to handle some of the really routine tasks that are out there for language processing, to do the vectorization that is described in the Word2Vec, as you can see here. And the particular purpose, though, of RASA isn't to do that basic entity extraction and so on. It is to do specialized elements like determining intent, which I have here mentioned in passing. Intent is dependent on context, and intent is a key element in conversational interfaces. If you open up a chat or you call into and interact with a voice bot, what is it you're trying to do? Are you trying to get information? Are you trying to find out how to return a product? Do you want to complain? Are you looking to make an additional purpose? So we try to understand intent. And that was an example there. Looking at elements of some of these other libraries that were mentioned there, again, just examples. John Snow Labs, Spark NLP, has named entity extraction, and you see it, the types of entities that are being extracted here, persons, organizations, and so on. Dates are not entities in my book. They're pattern-based, but in any case, this is the kind of stuff you can do, and this is free, open source. You can download it. If you have some programming skills, you can work with it pretty easily and directly. And in many cases, there are online demos where you don't have to do any programming at all in order to try it out. So an example here from one library, and this slide gives you a view of the variety of functions that the John Snow Lab Spark NLP package is going to handle, including the different transformer models that it handles, the different embedding methods that it handles, and then the functions that it produces here, including text classification, sentiment analysis, named entity, and so on. I want to look at the bottom right of the three columns of elements there. We have 330 plus pre-trained models in 46 languages, 90 plus pre-trained pipelines in 13 languages. There's a pipeline example in the bottom here in the black. It's a bit of Python code showing the application of Spark NLP to do some annotation of elements that are within a quotation that they put in here to show how easy it is to do this kind of stuff, because all of this is built into these software packages that are available. Let's take another example. Here for the Spark NLP, I see 330 plus pre-trained models. Here's a whole variety of models that Hugging Face's Model Hub has available to you. This is small text, and it's not easy to read. The point I'm trying to make here is the quantity, and I actually had to truncate the list here of models that are available from within these frameworks, let's call them, these software frameworks, models that are adapted to particular tasks and particular domains. Let's take an example. So an advantage of some of these tools is the set of models available and the pipelines available. So for instance, Hugging Face, here's one example, which I'm going to have two. The first example is text generation. And this is where you just simply implement a pipeline. A pipeline is a sequence of technical functions that understands this input text. The starting text is, as far as I am concerned, I will. And we want to have a continuation of this sentence. And it's very easy to get Hugging Face to do that. Now, here I'll go back to the box quotation. All models are wrong. Some models are useful. Let's just say, as the expression goes, your mileage may vary. The quality of what's generated here might not be the most wonderful in the world. Just another pipeline example, the Hugging Face pipeline for named entity recognition. You can see in the bottom half here, where we do a print statement, the types of entities that are identified by Hugging Face here, and then a score associated with the confidence levels. Now, often you're not going to want to use a toolkit because you're not doing direct data science programming or product development yourself. Instead, you're going to want to use a cloud toolkit. That's a very widely used way. So I just used one further image from that survey that Ben Lorica and Paco Nathan did to talk about cloud implementations that people are going to be using. And that varies by the sector, because certain sectors do have more stringent requirements or different requirements from other sectors. For instance, financial services and healthcare are both examples, elements of them, of regulated industries where they're going to have certain constraints about where data can be used and stored and all of that kind of stuff. So Google comes out on top here. Amazon's widely used, and here's an Amazon example, Amazon Comprehend cloud service. And in particular, a specialization. So I want to reinforce that the choice, I've said this twice already, the choice of model that you're going to have, the choice of service that you're going to use is often very dependent on the domain of information that you're going to be analyzing and the particular tasks that you're going to be doing. So in this case, Amazon Comprehend Medical is a service that helps you extract relevant medical information from unstructured text. And in particular, one nice thing about it, well, ontologies, which are networks of captured interrelated knowledge, are very widely used in medical domains, among other domains. That can include drug names associated with dosage levels. Amazon Comprehend is capable of consuming an ontology and applying it for the analysis purposes, which is the point I want to make in showing this particular slide. So domain adaptation is a very important consideration in the choice of tools that you're going to be using. A final use of that survey is to look at some of the criteria that people apply. This would apply not only for cloud service choices, but also for software toolkit choices, and furthermore for solution choices. Is it going to be affordable? Is it customizable in order to produce the accuracy and robustness that you need? Is the accuracy good enough either out of the box or when it's fully trained to meet your particular needs? And does it have the interoperability and data sharing capabilities? So these are considerations that people apply in choosing any type of software, and that can include cloud implementations, libraries, and also solutions. So I will get into a few solution examples next, not things that you're going to use for do-it-yourself, but rather things that you're going to use for particular business purposes. My own work focus tends to be around market research, customer experience, where you're analyzing surveys and contact center interactions. So I'm going to choose, I've chosen to show you 3 examples that come from that domain. And in particular, we're not just getting raw textual analysis here. We are getting something that is going to be useful in that domain. So an example here is Lexalytics, which I will characterize as the premier engine provider for sentiment analysis. In order to do sentiment analysis, you have to understand entities and topics and themes because the sentiment needs to be attributed to something. So they have their own little, well, simplified pipeline depicted in the lower left here of text preparation, extracting patterns, anything that sentiment can be attributed to. And then we try to understand the sentiment attributions. In the right side, they have a hotel pack is the one I've used here. They have other packs. Again, domain adaptation enables you to be much more accurate in order to understand the opinion bearing, the sentiment bearing words that are relevant in that particular domain. So we have that example. And then the upper left image just gives you an idea of the areas where they're playing voice of the customer and voice of the employees are not quite flip sides of the same the coin, but they're close to that. We want to listen to social media as well as handle formal documents like regulatory documents. And the aim in this business world is often called robotic process automation. What that means is to have a systematic automated handling of a process that a human might previously have handled. And humans can be in the loop there. So another example from the customer experience world is this company Clarabridge. They started around 15 years ago, and from their origins, they were a company that was very much rooted in text analytics technology. But what they've done here is to have a sentiment analysis that sticks the results up in a dashboard that we're very familiar with, but that shows an evolution of sentiment over time, and it shows sentiment interrelationships of the given term. You can see that in the scatter plot that's part of the dashboard shown here. And on the bottom right, we have something similar for customer effort. This is a really interesting notion of the idea that it matters to a customer how hard it is to do something. How hard was it to get the kind of support to resolve an issue that you have with a product by calling into a contact center or interacting with the company in different ways? Customer effort is a key human attribute, and that can be computed. It can be inferred from the text of interactions, from reviews, from survey responses, and other textual sources. So these companies are actually implementing NLP, and then they're implementing an analytical layer on top of what they've extracted via the NLP, sometimes very interesting features like sentiment and effort, and then displaying it in a dashboard type of form. And just one further example from Qualtrics, which was purchased last year, I guess, by SAP, although it's being spun off. And what I want to point out in particular here is the element with the horizontal bars that are red, gray, blue, that we have aspects here. Under claims, we have aspects such as claim submission, claim issues, documents, reimbursements. These are aspects of the claims process, and we do a sentiment analysis that is an aspect level here. It's not an entity, where the entity might be a particular document or claim, or it might be a particular product, but it is looking at process-oriented elements. In the customer experience world, we talk about the customer journey that ranges from learning about a product, purchasing it, trying to get support, all of these kind of things, maybe repeat purchases. We have different stages in a customer journey, and we want to be able to discern what those stages are and the aspects of them, and to do the analyses at these particular phases. So this is just a final example of natural language processing with analytics layered on top of it that is suited to particular business function or task. So the next segment of my talk, I'm going to get into areas that I focus on, in particular application areas. One is going to be emotion AI, and then the second is going to be computational AI. This was the talk that I first proposed to Adam, but I didn't want to do it at a full hour length, and I thought, well, why not go ahead and embed it within a larger talk about NLP. So what's interesting about emotions is that we have them. We display them in our face. This dates back to the 17th century, a French artist, Charles Lebrun. The expressions, emotions are interesting because they are not singular. Instead, they are what I'll call compositional. We see in the upper right image a mixture of admiration and astonishment. I don't know, May, do you agree with me that this is an accurate facial depiction of admiration with astonishment? It looks pretty good to me. So humans are emotional creatures, and of course that emotion doesn't occur only in our facial expressions, it also occurs in our speech and our text. So we have examples of emotion in this product review that I pulled from TripAdvisor. Who cares what show I saw here. That is a rhetorical and almost, yeah, it's a rhetorical question. It meant to establish a point. Remember, I talked about discourse analysis earlier as being interested, argumentation, and NLP is only starting to crack that. Every other aspect of the experience was awful. This person is angry. Exclamation point. That is an example of anger. Note the capitalized text in there. Shouted. This is an emphatic. It's the written equivalent of raising your voice and shouting. So we see emotion in online reviews. Another example lower left is just a snap from a research paper about psycholinguistic modeling in order to understand suicide notes. And we want to be able to predict the possibility, the propensity of suicide in order to try to prevent it. Third example on the right is from Twitter, which is of course a huge sense of emotion. Yeah, the top tweet there is, if only Trump supporters would be angry. Well, yeah, anger, but this is an attribution of anger to someone else as opposed to the person who's actually tweeting. So we'll get into that in a minute. And we have threads here. We have effectively a conversation. The bottom tweet, the bottom reply that is shown here is, I am so mad I can't sleep. This is a direct expression of emotion, and it is accompanied notably with an emoji that adds a whole other dimension to our analyses. So we have textual sources of emotion. The computability of this, the computability here dates really back 20 some words to work by Professor Rosalind Picard at MIT Media Lab, who wrote a book that I'll show an image of in a second on effective computing. Reading Roz's quote, if we want computers to be genuinely intelligent, to adapt to us and to interact naturally with us, then they will be need the ability to recognize and express emotions. Note both elements there, understanding and generation. A snap of Roz's book with some text explaining what the book is about, giving computers the ability to recognize and express, and in some cases have emotions. I'm not going to get into the philosophy of whether a computer can have an emotion or not. For me, it's enough for it to be able to simulate it, and you can get into an argument with Searle or Wittgenstein or someone else if you want to decide whether a computer can actually have an emotion. So work dates back there, and what we're trying to do is captured in this quotation from the Enlightenment figure Blaise Pascal: the heart has its reason that reason knows nothing of. We're trying to make computable the hidden feelings that humans have and experience and try to communicate incompletely. In order to do this, we need models. Yeah, I won't quote Box a third time, but keep him in mind that these models are imperfect. Here's a model that is very frequently used, one of only many models to cover emotion, Plutchik's Wheel of Emotions. It does convey the compositionality of emotions, that we might have dominance or optimism as a mix of multiple emotions. If we combine anticipation and fear, we get anxiety. It's compositional. And we try to get software implementations of this. Now, this field does date back, 17 years for one of the papers that I cite here about using natural language processing for sentiment analysis. Another one dates from 2008. I love the work done by the people on the paper on the right, Bo Peng and Lillian Lee. You can go out and find more if you choose to do that. But I will cite a source closer to home, and that is Bing Liu, who is at the University of Chicago, at the University of Illinois in Chicago. This dates to 2010, a representation as a tuple of sentiment analysis where we distinguish the object of the sentiment and the feature that we're looking at within that object from the sentiment holder. And we also notate the time of the sentiment. So in order to do this properly, we need to have entity extraction, or it can be more sophisticated since 2010 than just entities, and can be topics, themes, and aspects. And we need to extract relations in order to be able to attribute the entities, to be able to attribute a given sentiment rating to an entity, and also to understand who the sentiment holder is and all of that. As being noted here, none of this stuff is a solved problem. So fast forward 5, 10 years, and I clipped this from a presentation I'll cite later, of not looking only at sentiment, but looking at emotion. So sentiment is typically a positive, negative, neutral rating versus emotion, per that Plutchik illustration that I showed, can have many emotions that are much finer grained. Where this started to come out to the front was in the last 5 or 8 years, when computing power made the emotion a tractable target for analyses, where we could do more than just a positive, negative, neutral classification. So we have emotion that, again, is temporal. It has a time that it's felt, because the emotion of a given emotion holder or feeler can change over time, obviously. So here to systematically define emotion AI, and this is my definition, except for the first one that's in quotes, we have emotion understanding, call that emotion mining, and we have emotion synthesis, to have the machine provide contextually appropriate responses that convey emotion that is appropriate to the words that are being used, and appropriate to the facial expression if we're also having a simulation, an avatar or a robot or something. And the emotion also, the words have to match the tones of speech. And emotion induction is something, of course, that advertisers have been trying to do for many, many years to make you feel something. Authors try to do that as well. The starting point for sentiment and emotion work has been lexicons, lists of words with their emotion associations. Here's some work by Saif Mohammed from the National Research Center in Canada. You can go out and find it yourself. And one further slot from Saif Mohammed showing the hierarchical nature of emotions, which he calls affect categories. Remember, Roz Picard's work was affective computing, dealing with personal states. So affect here is mixing negative and positive, but also high-level emotion categorizations in a hierarchical arrangement where we assign emotions to a category. Now, this is not always so simple. I will just cite an example. I don't have the slide here that I've used before, but think of a figure such as Kobe Bryant, the basketball player. Yeah, he was killed while doing, he was killed in a helicopter crash just a little less than a year ago, wasn't it? And you can feel sad about Kobe Bryant and his death, his premature death, and his daughter and other people as well. But that in effect is a positive emotion. Sadness in this case is a positive emotion. It would be, if I didn't feel sad about Kobe Bryant, that would be a negative thing. So things are not always straightforward. So we do apply some stats to looking at emotion distributions. Here's an example from a paper where R was used for that. R is nice for visualization. We look at emotion trends over time, and the source here is extracted from text from shareholders, but there are a lot of complications. A final citation of a slide of Bing Liu's. This is from a conference presentation he gave for me back in May, a conference called the Emotion AI Conference, where he talked about intensifiers, behaviors that are associated with emotions. There's no emotion that is explicitly specified in "he cried after he saw his mother," but it is implied or implicit here from the behavior that is described. And sarcasm is something that people bring up an awful lot. And it conveys something that maybe is not commonly called emotion, but is a human sense that is very frequently associated with it. This is implemented in software. An example here is IBM Tone Analyzer, which has been out for quite a few years, where we note here that there are nuances here. Writing tone, social tone, emotion tone. Perhaps Shlomo Argaman will get into some of this stuff in his stylistic analysis talk that follows mine. And we understand once again that there is a complexity here, that there are multiple emotions or feelings that might be felt. So obviously you can go license Watson yourself. You can go out there and try some of their online examples. And just finally, words aren't everything, and they're not enough. We have idiom. I mentioned idiom translation, the conversation I had with Rohini Srihari earlier in my talk. We have the conventions associated with particular medium like Twitter here. We have personality. We can do persona classification based on text. We have something that's implicit in the communicative act. What does it mean when Alyssa Milano, now she has a certain identity that comes into play here. What does it mean when she writes, "just going to leave this right here"? That is idiomatic expression, and it expresses a certain disdain, which is similar to the emotion expressed by Donald Trump in this photo with the smirk that's on his face, a disdain. So we have multiple ways, and part of my point in putting this out here is to reinforce that when you have multiple data sources that can be analyzed in conjunction because they're correlated in time, words with facial expressions, with speech tones, then you're going to get more powerful analysis, more accurate and analytical capabilities. So we have a communicative act here. Why did this person choose to stick this tweet out there? And then further, we should look at the network effects. How are things like this shared, and what impels someone to share a bit of content or view? Final example, we'll talk about conversational interfaces. You'll hear a bit more about this later from someone else. One of those toolkits, and I talked a little bit about RASA for intent extraction. Yeah, we have a depiction of a chatbot conversation here, where what's important here is when you're dealing with contact centers and customer interactions, we talk about the next best action. What should I do next? That applies whether you're an operator in a contact center or whether you're a bot trying to figure out how to respond to someone. We need to understand what the person's intent is and what we should do to try to satisfy that person's intent. Another example here from core.ai shows the sentiment attribution to elements within a customer interaction that can influence the next best action, how the bot is going to reply. RASA, interestingly, by the way, does have capabilities for speech to text and text to speech in order to enable this technology that's designed for purely textual interactions to be used in a voice interaction context. So one more slide on RASA. I thought this was interesting, describes what they do on the left there, but the image on the right is from a blog post from 2 years ago, so it's not quite current, talking about the different types of assistants that are possible with the technology that is out there and that is in the pipeline. So for instance, 2 years ago, they talked about autonomous organization of assistants to be out there, in 10 years in the future. So we do see an evolution of the technological capabilities based on more data available, data used more effectively, models that become much more powerful and that become more implementable through the distillation processes that I mentioned in passing earlier to handle common business problems. So I said that RASA can be used for speech-based conversations via text-to-speech and speech-to-text. There are reasons for doing this. Here's a bit of a study from a year ago from VoiceBot AI that found that customers are much more responsive. They're much happier when they're talking to a human rather than a synthetic voice. So it says to us that we should try to make our synthetic voices more human, to make them more emotional. Well, how do we do that? What are the components of speech? And this is part of natural language processing to understand the speech and not just the textual component. That includes the frequency or the pitch of speech. And I'll mention, by the way, that is change and not just the pitch at a given moment. If something becomes higher pitched, it indicates, over the course of a conversation, it indicates something. Similarly, the speech rate, which is mentioned here under number E, the temporal aspects, the intensity or the loudness. There are other elements, prosodic. Am I repeating myself? Do I find myself saying the same thing over and over? Don't you understand? Do I have to say it again? Yeah, you get the idea here. So we have speech elements that come into play. Of course, machine learning is being used to try to render voices with the right tonality, the right emotions, and so on. That can be rule-based, as indicated here. Again, dimensional space. Well, there we go back to our old vector spaces stuff. Or it can be something that is intended to just work, like what's possible right now with the Amazon Alexa, with the Echo and Dot devices, where there's markup. Yeah, you just mark up some text in order to get it to convey that text with the emotion that you're indicated in the markup, because we want things that are just going to work while we pursue the rich research agenda of the type that I showed for EMNLP earlier. I mentioned Bing Liu's talk at my conference back last May. Here's a link to it. You can watch his talk online if you want. He is a great resource right there in Chicago. And I'm going to provide my slides later. Actually, I can go and find the slide share right now in order to paste that in. And which I'm doing right this second. And then finally, where we're going with this conversational AI, speech, emotion infused conversational AI via products like Oliver API from behavioral signals. It looks like I have just about eaten up my time. I went a little longer than I planned to, but maybe I can take a question or two if anyone has one. Vinod, you had a question earlier about neural networks using parse trees and so on. I'm actually going to duck that question because my intent here was to try to not to cover the ins and outs of the underlying technology, but parsing is very important, in particular to understand dependencies of the different elements that are being parsed in order to infer relationships. I'll just leave it at that. Can I take maybe one question or two?
Sure, yeah, we can take one question, Seth. Does anyone else have a question? Seth, I had a quick question if no one else has a question.
Yeah.
Does that? So it seems to me just in your talk, well, prior to this, but your talk kind of reinforces that it really seems like NLP, maybe more than other areas of statistics or machine learning, is really being driven by non-academic institutions. You know, you cited Google, IBM, et cetera. I mean, is there something about, do you agree with that? And is there something about NLP that kind of makes that the case?
So yes and no. You know, it used to be that the NLP people were coming out of computational linguistics departments. I can think of several examples. One is my friend Philip Resnick, who's a professor of linguistics at the university and computer science at the University of Maryland. But I think of another guy I know, Jason Baldridge, who is was at the University of Texas and did great work there, but then he joined Google maybe about 5 years ago. So we see academics who really do understand that there's a huge amount of really interesting work being done at Google. I interact with people from Facebook AI, at all sorts of companies, but we do see a lot of people in academia who are consulting or working with commercial product companies in order to do commercializations of their products. Some academics like Bing Liu I mentioned are quite happy to stay in academia, and I do know that Bing consults with some companies. James Pennebaker from the University of Texas is another example. I could probably give you a slew of them, but yeah, loads of interesting work being done in academia, often, very often in cooperation with commercial technology leaders that are making products out of these things.
Okay, great. Well, Seth, thank you very much. That was a great overview talk to really ground us as we move on to the other application areas later today. Thank you very much.
I'd love for people to get in touch with me if they have further questions or areas where I can help. And thanks for inviting me.
My pleasure.